iniciado aí a fase tão importante do evento, que é de networking, encontrar os colegas, trocar ideias. Vamos aproveitar cada break que a gente tenha. Mas agora, voltando aqui, dando sequência à nossa sessão de abertura e plenária do EMECR, teremos 3 palestras agora muito bacanas, selecionadas aí especialmente pela comissão organizadora, para trazer alguns ângulos e perspectivas aí de vários esforços, tecnologias, rotas produtivas que a gente tem aí para descarbonizar o nosso setor. Iniciando, então, é um grande prazer aí para a ABM de convidar o Ricardo Carvalho Nascimento, que é o CEO da Aço Verde do Brasil. O Ricardo vai fazer uma palestra sobre Aço Verde do Brasil, the world's first carbon neutral steel plant. O Ricardinho está aí.
Agradecer a presença de todos, parabenizar aí a ABM por mais esse encontro. É muito importante aí para o desenvolvimento da siderúrgica nacional e mundial. É um prazer muito grande estar aqui apresentando esse case, que é a AVB, Aço Verde do Brasil, como a primeira produtora de aço carbono neutro do mundo. Bom, a AVB é do Grupo Ferroeste. A gente tem essa questão de sustentabilidade no nosso DNA, uma vez que todas as nossas atividades possuem como biomassa as fontes de energia. O Grupo Ferroeste é historicamente um produtor de ferro-gusa e sempre utilizou o carvão vegetal nas suas operações. A AVB hoje tem uma capacidade instalada de 600 mil toneladas de aços laminados e gera, no Maranhão, 2.300 empregos diretos. Uma coisa interessante é que essa rota carvão vegetal, até então, é uma rota intensiva em mão de obra, fazendo com que o desenvolvimento socioeconômico chegue através de emprego e renda em populações desprovidas de qualquer desenvolvimento, como no interior de Minas, no interior do Maranhão, no interior do Piauí, locais onde que o índice de desenvolvimento humano e IDH são os mais baixos do Brasil. Bom, essa é uma foto da unidade industrial, né? São 2 altos fornos, uma cearia com convertedor a oxigênio, a laminação, as suas plantas de água, né? E as mais diversas utilidades necessárias para a operação de uma cearia integrada. A região onde nós resolvemos instalar a AVB é uma região pouco desenvolvida. Então, para se ter uma ideia, foi-se necessário a instalação de uma linha de transmissão de 70 quilômetros para abastecer essa unidade de energia elétrica. Bom, agora um pouco mais do mesmo. Nós estamos localizados em Açailândia, no sul do Maranhão. Hoje vendemos o aço em todas as regiões do Brasil, desde o Rio Grande do Sul, Rondônia, Roraima, e temos uma presença muito forte com os nossos clientes, uma vez que nós iniciamos pelos aços de médio carbono e agora já começamos a produção de aços de baixo carbono e agora, mais recentemente, aços de alto carbono, abrangendo, então, toda a cadeia do fio-máquina. Bom, a razão principal de eu estar aqui hoje, né, não é por ser uma empresa nova ou ser uma empresa grande, mas sim uma empresa verde. A siderurgia talvez enfrenta dos maiores desafios da indústria, porque ela é necessária para o desenvolvimento humano, até então insubstituível, e a tendência, as expectativas, é que a produção de aço no mundo cresça em torno de 50% até o ano de 2050. O que parece ser uma previsão acertada, uma vez que para esses processos todos necessários de economia verde, vão se precisar construir novos carros, novas fábricas, novas fontes de energia, e todas elas consomem aço. Para se descarbonizar, uma palavra que eu aprendi hoje, errada, e desfossilizar seria a palavra mais correta, mas para se descarbonizar, estima-se investimentos de mais de $1 trilhão. Esses investimentos, por si só, já aumentariam o custo do aço enormemente. Isso sem contar os custos de produção dessas novas tecnologias que ainda estão todas por se desenvolver. E quando a gente fala 2050, a gente imagina ser um período longo pela frente, em compensação está logo ali. Haja vista que qualquer indústria siderúrgica, para se construir dentro de uma tecnologia já dominada, demanda mais de 5, 6 anos. Imagina para se descarbonizar todo um setor em 25 anos. Ou seja, nós estamos correndo contra o tempo. Esse esforço global, ele vai exigir com que todos os pares, todos os órgãos se unam em prol dessa descarbonização, porque não necessariamente vai ser pelo esforço do mercado, pelo esforço da indústria, pelo esforço dos governos, né? Vai demandar um esforço conjunto global. Uma vez que só a siderurgia representa 7% das emissões mundiais. É muita coisa. E das emissões industriais, a siderurgia representa 24%. A média global hoje, por tonelada de aço produzido, está em torno de 1,8 toneladas. Isso porque existem basicamente 2 formas tradicionais de se produzir aço. A primeira, através dos altos fornos a coque, que tem uma emissão média em torno de 2,2. E a segunda, através da reciclagem da sucata, altos fornos elétricos, que tem uma emissão média de 0,6. E a média de todo o setor está em 1,8. Então, bom, vamos diminuir as emissões, vamos nos esforçar e aumentar rapidamente a transição de coque para a reciclagem da sucata. Isso certamente vai ser um primeiro caminho, certamente vai ser super utilizado. Nos Estados Unidos, hoje, existe uma transição forte nesse sentido, muito investimento na indústria de base elétrica, na indústria de reciclagem, mas certamente a abundância e a disponibilidade de sucata, a disponibilidade de energia elétrica limpa, são os grandes desafios dessa solução, e eu estou certo que não existe solução única e solução definitiva. Terá que ser um conjunto de várias soluções. Bom, falando em várias soluções, nós podemos passar por ações de eficiência dos altos fornos, né? A carga de sucata no topo dos altos fornos, aonde que nós temos aí uma sobra energética, isso poderia reduzir as emissões, o uso de DRI, o uso de PCI com biomassa. Eu acho que o Brasil hoje é um país abençoado nesse sentido, né? A abundância de biomassa no nosso país permite com que as soluções mais dominadas sejam aquelas que nós temos abundância, que é o caso da biomassa, né? Nós temos soluções de captura e estoque desse gás carbônico. Nós temos as soluções do uso do hidrogênio para redução direta, né? Em compensação, como eu lhes disse, não existe solução para esse desafio. Não existe solução única. Cada país, cada região vai ter que usar os seus potenciais e contribuir com a sua parte. Bom, já me perguntaram muito, né? Poxa, mas você, carbono neutro, como carbono neutro? Isso foi uma decisão, acho que acertada, que a gente teve na indústria, né? Que foi a reutilização de todos os gases de processo, a reutilização de vários resíduos e, obviamente, nós fomos agraciados pela escolha do carvão vegetal, que também vem de uma condição histórica do nosso grupo, como produtores de ferro-gusa a carvão vegetal. E, a partir do momento que a gente encontrou um protocolo que pudesse ser certificado, um protocolo que pudesse comparar a gente com pares no mundo inteiro, nós tomamos a decisão de utilizar esse protocolo. Qual protocolo é esse? É o protocolo GHG. Esse protocolo é o protocolo utilizado pelo IPCC, que é o painel intergovernamental de mudanças climáticas da ONU. Esse painel, eles criaram uma metodologia de cálculo. E esse painel, ele mensura todas as suas emissões, tá certo? Do portão para dentro da usina. Por que isso? Mas você não vai considerar a sua floresta? A floresta é altamente geradora de créditos de carbono. Bom, mas a floresta, a produção do carvão vegetal para o uso siderúrgico é uma jabuticaba. Só tem no Brasil. E eu não posso utilizar um método, uma metodologia de cálculo que não possa ser comparável mundo afora. Então, eu tenho que usar o que já existe. E o que já existe é essa metodologia GHG, né? Ela é facilmente encontrada pela norma ISO, está aí o número da norma ISO, 14064, tá certo? Que ela mensura todas as suas emissões a partir das matérias-primas que você utiliza, os resíduos que você recicla e os produtos que você produz, tá certo? E essa metodologia utilizada, ela nos quantificou em 2018 com 0,10. Na hora que a gente viu esse número, a gente falou, opa, nós estamos muito perto. Vamos entender exatamente o que isso significa, tá certo? Vamos ver quais ações que a gente pode melhorar para a gente chegar na condição de neutro. E nós conseguimos chegar na condição de neutro em 2020. E para vocês verem a dificuldade, né? Em 2021 a gente já não foi neutro. A gente foi 0,2. Então é difícil. Porque qualquer emissão ou qualquer tipo de produto fóssil que você venha utilizar a mais, ou qualquer resíduo, as escórias que você deixa de reaproveitar em algum outro processo, elas geram emissões e isso é ruim, né? Então nós tivemos uma piora em 2021 em relação a 2020, mas já temos um plano de ação forte para que isso, né, não aconteça, né? Bom, nós temos uma indústria chamada CBF, que é uma indústria de ferro gusa, operacional desde 1986, né? E um ano depois nós resolvemos medir as suas emissões, em 2019, né? E ela é carbono neutro também. Então, de uma forma bem simples, utilizando o protocolo GHG, qualquer usina siderúrgica brasileira que utilize carvão vegetal e tenha uma fonte de energia elétrica limpa, ela é ou neutra ou quase que. As emissões se dariam nos processos subsequentes, na cearia e na laminação. Certo? Então, para a CBF, conseguir a condição de carbono neutro foi muito mais uma condição de mensuração, de metodologia, do que qualquer coisa. Não houve um esforço, e sim o próprio processo permitiu com que a gente conseguisse essa certificação. Já na AVB, não. Os processos de transformação do ferro em aço e do tarugo em laminados, esses, sim, são carentes, são dependentes de energias fósseis, e para que a gente tivesse essa independência, a gente teve que fazer uma série de investimentos desde a origem do projeto. A exemplo do uso do gás de alto forno para reaquecer os nossos tarugos, todas as usinas siderúrgicas do mundo, praticamente, utilizam alguma fonte fóssil para reaquecerem o seu semiacabado e fazer a laminação. No nosso caso, a gente utilizou uma tecnologia chamada regenerativa, e essa tecnologia permitiu com que os gases oriundos do nosso alto forno a carvão vegetal fossem suficientes para reaquecer o nosso tarugo, e com isso a gente conseguiu vencer o último desafio que a gente tinha e tornar carbono neutro. Bom, então essa é uma comparação do que a AVB é atualmente com a média mundial. Existem outras empresas fazendo carbono neutro, mas não em escala comercial, né? Em escala comercial, a AVB é a primeira, e em função disso, a S&P Platts nos condecorou, nos premiou com esse prêmio ESG Breakthrough o ano passado. Bom, quais foram as ações que nos levaram a uma condição de quase neutro para neutro? Nós utilizamos 100% do carvão vegetal nos altos fornos. No passado, a gente utilizava um pouco de coque e tal, e nós zeramos o uso de coque, 100% de carvão vegetal. passamos a reciclar 100% da nossa escória de alto forno numa produção de cimento própria. Ou seja, a partir da utilização dessa escória, fontes virgens que, para a sua obtenção, geram CO2, deixaram de ser utilizadas. Então, pelo processo de GHZ, isso gera créditos. E nós adquirimos um gasômetro para reutilizar toda o gás de convertedor nos processos de aquecimento de panelas, de tandes, de sucata, na AVB. Isso foi em 2018. Em 2019, a gente conseguiu performar esse processo regenerativo no aquecimento de tarugo, no reaquecimento de tarugo, e com isso nós eliminamos 100% o enriquecimento do gás de alto forno com GLP para reaquecer o tarugo. Hoje a gente não utiliza qualquer combustível para enriquecer o nosso gás. E a gente passou a consumir, a comprar energia elétrica através de contratos exclusivamente de fontes renováveis. Em 2020, nós passamos a reciclar a escória do alto forno, do convertedor nos altos fornos, substituindo calcário e substituindo parte do minério de ferro. Espero que a Vale não esteja escutando, né? Mas, com isso, a gente conseguiu reciclar 100% da escória de alto forno, de aciaria, 100%. Nós somos uma indústria que opera a nossa aciaria desde dezembro de 2015 e nós não temos mais do que um montinho do tamanho dessa sala aqui de escória de aciaria no nosso pátio de escória. 100% da escória de aciaria é reciclada. Bom, quais são as ações para frente? O que a gente quer fazer para melhorar a nossa condição, né? A gente vai utilizar o gás de alto forno para gerar eletricidade, que é uma prática usual dentro do grupo nosso. Todas as nossas indústrias já o fazem isso. E então a gente tem essa sobra de gás lá, nós vamos usar toda essa sobra de gás para gerar 1/3 da energia elétrica que a gente consome. Estamos num processo muito avançado de testes de um novo forno para a produção de carvão vegetal. A siderurgia a carvão vegetal, ela está engatinhando. Ela é um bebê que tem uma vida inteira pela frente. A siderurgia a coque, ela é um senhor que precisa de tomar todos os tipos de remédio, ela precisa de dar um jeito de ficar mais jovem. A indústria carvão vegetal hoje, ela é altamente ineficiente e tem inúmeras coisas que ela pode fazer para melhorar os seus resultados. E muitas pessoas perguntam, poxa, como você consegue reciclar tanto os seus resíduos? É pelo único fato de que, a partir do momento que eu não utilizo um combustível fóssil, os meus resíduos não possuem uma série de contaminantes super tóxicos, super perigosos, e que você dificilmente poderia utilizar de uma forma circular. O carvão vegetal permite isso. Então, esse projeto do forno industrial, ele tem o potencial de melhorar a conversão nossa, madeira-carvão. A nossa indústria hoje, a média, é uma conversão seguinte, ela usa 1,35 metros cúbicos de madeira para fazer 1 metro cúbico de carvão. Esse metro cúbico tem em média 250 quilos. E ela usa 650 quilos de carvão para fazer 1 tonelada de gusa. Certo? Nós temos a possibilidade de chegar num índice de conversão madeira-carvão de 1:1. Isso faria com que a nossa necessidade de área plantada reduzisse em mais de 30%. Nós poderíamos reaproveitar o alcatrão, que representa 12% em peso da madeira seca, e hoje ele é 100% descartado. Só esse alcatrão aumentaria o rendimento nosso, que hoje é de 25%. A gente gostaria que ele chegasse em 40%, que é o rendimento gravimétrico, e se a gente arrumasse uso energético para o alcatrão, ia para 52%. Então, o que eu estou dizendo aqui para os senhores hoje é que o carvão vegetal tem a chance de dobrar o rendimento em pouco tempo. Qual é a chance de melhoria da indústria coque? Que já está há 100 anos luz na frente do carvão vegetal. Que todo recurso, toda a tecnologia do mundo já foi implementada, né? Então, esse forno vai melhorar o nosso rendimento carvão, madeira. E muita gente fala, poxa, mas carvão vegetal não dá escala. Carvão vegetal é muito difícil. A indústria de celulose no Brasil produziu 21 milhões de toneladas de celulose em 2020. 21 milhões de toneladas de celulose são 80 milhões de metros cúbicos de madeira. Se esses 80 milhões de metros cúbicos de madeira fossem utilizados com os índices gravimétricos que nós temos hoje, não é o que nós gostaríamos de ter, não. É o que nós temos hoje, que é 1,35:1. A gente poderia produzir 32 milhões de toneladas de aço. Ou seja, a indústria de celulose brasileira teria condição de alimentar a indústria siderúrgica brasileira com eucalipto. Então, isso não é um sonho. Hoje, qualquer projeto de celulose possui o tamanho do projeto de celulose, a escala, é 1.200.000, 1.300.000, até 1.500.000 toneladas de celulose. Isso é suficiente para produzir 2,5 milhões de toneladas de gusa. Se a indústria de celulose pode, por que a gente não pode? Será que eles são melhores do que a gente para plantar floresta? A tecnologia da silvicultura está aí. Nós temos a área plantada. Inclusive, para as pessoas mais antigas, lembram dos planos de governo de fomento à silvicultura no Brasil. A área plantada brasileira hoje é menor do que ela era 40 anos atrás. Então, o que falta, na minha visão, é o comprometimento da indústria siderúrgica e o comprometimento do governo em entender que carvão vegetal é uma boa opção. Nós estamos também com um projeto esse ano, nós estamos construindo um projeto de briquetes para reutilização de todos os nossos resíduos que a gente ainda não consegue destinar, que basicamente são a lama de alto forno, o pó de balão e a carepa. Com esse briquete, a nossa ideia é que em 2023 a gente seja também a primeira usina siderúrgica livre de resíduos sólidos. A gente quer ser uma usina livre de resíduos sólidos. Uma outra solução que a gente está dando também é que quando a gente brita a escória de aciaria para botar no alto forno, ela gera um pó. Esse pó, por ser de carvão vegetal, ele pode substituir o calcário na agricultura, porque ele é rico em calcário, ele é rico em magnésio e, principalmente, com essa falta que nós estamos tendo de fertilizantes, ele é rico em fósforo. Ele tem quase 2% de fósforo. Só em termos de fósforo, ele vale R$80 por tonelada, com os preços de fertilizantes atuais. Bom, o número 5 é também a questão do uso de fertilizantes orgânicos. A gente quer usar as escórias nossas, que a gente ainda não consegue usar de madeira forte, que é o finos da escória de aciaria, a gente quer utilizar para agricultura. E com isso, fazer adubo orgânico, esse tipo de coisa. Então, tem várias coisas para acontecer aí, e começaram em 2021, e, se Deus quiser, vão estar 100% operacionais até o final do ano que vem. Bom, eu já disse isso, né? A AVB é carbono neutro do portão para dentro. Ah, mas e do portão para fora? Você não tem as florestas? Né? Bom, nós temos as florestas, mas, até então, não existe metodologia para a mensuração do quanto você fixa de carbono na floresta, do quanto você emite de carbono no processo de carbonização. Então, esse balanço ainda não foi pacificado. Não existe uma metodologia pacífica para ser utilizada hoje no mundo. Mas, pelas nossas estimativas, se os nossos cálculos estiverem corretos, para cada tonelada produzida de ferro-gusa a carvão vegetal, você retira em todo o processo até a redução, você retira 1 tonelada de CO2 do meio ambiente, fazendo com que esse gap entre o atual e o vegetal, ao invés de ser de 2 toneladas, ser de 3. A localização nossa, a questão socioambiental nossa, e muito obrigado mesmo.
Hello, everyone. Thank you so much, Jose, for having me. It's such a pleasure to be here. I'm sorry I can't be speaking with you in Portuguese, but I hope the translation is good. So there was a bit of a preview to this presentation that we gave yesterday, and one of the participants in that roundtable brought up how difficult it is to model everything and how forecasts are always wrong. And we said, well, we just strive to be the least wrong of anyone. So what I'm going to do is to walk you through how we've done our modeling for a green steel transition. And you can tell me where you think I'm more wrong or less wrong afterwards. For anyone who doesn't know who BNF is and what we do, we're a global company. We're part of Bloomberg, but we're the clean energy research segment of that business. So we do the kind of work that a think tank would, but more focused on the private sector, on costs. So we talk a lot more about the cost of green steel and a little less on policy recommendations than a typical think tank would. The thing that makes my job a lot easier is that we have so many people working on every portion of the energy transition. So I can talk to our experts in the power sector and in the transport sector to give a view not just on how industry is changing, but how the global energy system is changing along with it. The world is pretty different from when I started in sustainability. Then we were the slightly odd people at all the conferences, And today we get a lot of questions about things like this. So today, most of the world's emissions are covered by a net zero target. And that has given every company and every industry in each of these countries a mandate to get to net zero. So what then started happening is that countries realized they weren't going to have anywhere to hide. And so they started putting their own net zero targets in place. When we first started counting this, steel was in the lead, and now they've been overtaken by plastics and cement, but there's still a lot of time to catch up. So we think that about half of the world's plastic manufacturing capacity is covered by net zero, and for steel, that's about a quarter. But of course, a lot of this depends on what companies in China do. What goes along with those net zero strategies are individual companies' abatement strategies. So this is what several of the leading steelmakers want to do in net zero. You can see that pretty much everybody agrees on circular economy, so more recycling, and everybody agrees on becoming more efficient and improving their processes. Where things get really different, where these companies start to differentiate themselves, are in the revolutionary technologies, so the things that are just emerging today. Some have really put a stake in the ground and said, hydrogen is the way I'm going. And that's particularly a European strategy because there's so much policy support there. And others like ArcelorMittal or ThyssenKrupp, they're saying, let's take a broader view. Let's see what's out there. Let's try a bunch of different things. We don't think there's one right answer. We've done our modeling at a global scale, but today we're working on doing that at a country level. And steelmaking is incredibly dependent on the resources that you have at hand. And so it's going to be different for each country. The other thing to bear in mind is that not all net zero paths are equal. It's very simplistic to just say, let's get to net zero by 2050, because the amount of warming that you end up with varies depending on how much reduction you do when. So you can see if we carry on mostly as usual, if we make some changes when things get cheaper, if we wait and see, we're looking at something more like 2 degrees. If the world wants to be very ambitious and get to 1.5, those changes have to start right now. There has to be a significant reduction in the next 10 years. And that really dictates what kind of technologies you want to invest in and when. But if we look at just the steel industry specifically, it's pretty far from any kind of net zero goal. Usually at BNF, we are modeling out to 2050. That's our usual stopping point. But when we did that for the steel industry, and we saw that we were expecting emissions to be higher in 2050 in many cases than they are today, it was too depressing. So we went out to 2100 to see if things would get better. And they do. And that is mostly because we think demand for steel starts to drop after 2045 or so. That's because you're in a replacement cycle rather than having a lot of countries building anew. So that naturally starts to bring your emissions down. You see a lot more recycling in developing economies because they finally have the steel scrap domestically that they need. So you do see a big emissions drop, but well beyond 2050. You can reduce the intensity of your secondary steel production by using clean energy. That gets you a bit of a drop, but you're still not at zero. That's the purple line. And then if you really try from 2030 onwards to change primary production, you get to the green line. So you're lower, but you're still not at zero. In order to meet net zero by 2050 or 2060, you have to be in that gray band. And all of our scenarios were pretty far from that. So that's why we started looking at what needs to happen today and in the 2030s and in the 2040s. So you do the easy things first. You recycle more, you switch your EAF plants to clean energy. That makes sense. By 2030, you have to start doing more of the harder work. So your existing plants start to blend in hydrogen, and new build is mostly direct reduction. By the 2040s, we think most of the capacity would be hydrogen or molten oxide electrolysis. That gets you to this, a net zero supply curve for the steel industry by 2050. We went through and we calculated how much it would cost to make steel, whether you were retrofitting a plant or building a new one, for several different technologies: hydrogen, offsets, recycling, CCS, and electrolysis. And this is what we think makes sense based on the replacement cycles that we're expecting to see in the industry. There's a lot of hydrogen there, and there's a lot of recycling, and there's some retrofitting of CCS in certain places where the policy is favorable to it. This is a big change for the steel industry, especially that massive green hydrogen block. And I know a lot of you in the room are going to disagree with me, but this is what the world could look like by 2050. I don't expect you to be able to read any of this. This is just to show you that we take a lot of different financial and technical variables into account. We built this model, and we've made it available to people who want to use it to calculate how much green steel would cost using a number of different technologies. So you can set a return, you can look at a price, you can even include some carbon pricing if you want to. We didn't, we keep policy out of it. That's way too hard to predict. So what are those technology options? And what were some of the assumptions that we had to make along the way? You've had a great overview of most of these things from the speakers before me. So I'm going to dig into a lot of the numbers and talk more about the bottlenecks and the headwinds. Costs for green steel are pretty high right now. The reason why we see any companies doing this at all is because their customers, like automakers, are willing to pay a pretty hefty premium for it. That's because they want it right now. The technologies that we focused on were using a natural gas DREAF with offsets, recycled steel, hydrogen, CCS, and then electrolysis as a kind of dark horse on the horizon. They're all a lot more expensive than today's production costs, which is the gray box. Recycling and offsets maybe have a chance. But by 2050, things change a lot. And we think that hydrogen could become the cheapest way to make steel. This is the only way we've ever seen things change because of sustainability. We've been tracking wind and solar and electric vehicles for a long time now. And it's always the promise of being cheaper than the incumbent that makes things happen. That's why you see so much hype around hydrogen, especially in Europe. It's charts like this and an expectation that it's going to get very cheap. So let's look at all of these different options and what we see happening with each one of them. Let's start with recycling, what should be the easiest thing to do. The good thing there is that we think renewable power costs are going to fall pretty significantly by 2050. So we normally say the power is about $60 a megawatt hour today, and then renewables get to 30 or 40 by 2030, and then they're more like 10 to 20 by 2050. So that intermittent renewable can be a really cheap way to power your EAF. But the problem is that doesn't matter too much, because in the chart on the right, you can see that the levelized cost of this green steel doesn't depend very much on electricity. What it really depends on is your scrap price. Scrap prices haven't been too much lower than hot rolled coil prices in most places. And that is making the economics of recycled steel very difficult, especially in places like China, where they have a policy mandate to do a lot more of it. So there has to be some kind of incentive in many countries, or a lot of investment in the scrap supply chain. Despite all of that, China still wants to build a lot more EAFs. Now, maybe they won't use 100% scrap in them, but this is the switch that we're starting to see. Policy is very favorable towards EAFs in China, and that's because the Chinese government recognizes that they need to change over their infrastructure. They want something that can be cleaner because they're facing a lot of pressure to reduce air pollution, especially in the winter, and that is causing a move away from blast furnaces. Very slowly, but a move all the same. Okay, let's look at hydrogen. We think that hydrogen-made steel is going to be able to compete with today's production methods if the cost of hydrogen falls. So today we think it's about 5.5 dollars per kilogram for hydrogen in most places. By 2050, we think it could be about $1 a kilogram, and that pushes your costs into a range that looks competitive with how steel is made today, even in existing plants. But the question is, how do you get there? And how do you make sure that those cost reductions actually happen? 2050 is a long way away. Hydrogen is a very new technology. This is where we think hydrogen costs are today for a huge number of the countries that we model. The way that we did this is to model both a Chinese electrolyzer, which is much cheaper, and a Western electrolyzer. That's the top and bottom of each of those bars. And then we've chosen for each country whichever is the cheapest form of renewable power, whether it's wind or solar. And then we've matched the electrolyzer capacity to the capacity factor of your wind or solar. So you're only making hydrogen when the sun is shining or the wind is blowing. And that's how you get to these prices. So that's today. Things look different by 2030. All of the prices and costs are much lower. The countries are mostly the same, but there is a lot more solar. And that's because we think solar will come down much faster than wind. So by then, especially in places like Brazil and Chile and Peru, hydrogen is starting to look like it could be competitive with natural gas, and it's starting to look like where we need to be in the chart I showed you a couple of slides ago in order to be competitive. Now, normally when I put this slide up on the screen, somebody gasps, so thank you for your restraint. But definitely everyone starts comparing notes and talking about how they think we're getting here. The answer is that we're getting here because we've seen supply chains move very quickly to the cheapest form of production and to scale up. We've seen that in solar, we've seen that in batteries. So we think the cost of the electrolyzer stops mattering pretty quickly because they get cheap. So then it's all about the cost of electricity. We've been looking at renewable power CapEx and electricity costs for 10 or 15 years now, and we've seen them marching down and down and down. COVID was the biggest disruption we've ever seen to supply chains and to the way the electricity system was operating. And even that caused a little bit of an uptick in CapEx for wind and solar, but we didn't see very much of an impact on installations, which are ultimately what drives those cost reductions through economies of scale. So that's why we're confident in these numbers, because it all depends on electricity, and we know wind and solar pretty well. The biggest uncertainty here, the biggest thing that I think would change all of my forecasts for the cost of hydrogen-made steel, is how much hydrogen you actually need to make steel. We see a lot of academic estimates that are between 50 and 65 kilograms per ton of steel. But academic estimates are often a best case, and the real world is quite different. So for the projects that have been announced from Baowu in China and POSCO in Korea, the numbers are much higher. They're saying something like 80 kilograms of hydrogen per ton of steel, or almost 100 from POSCO. Now in 2021, that's just the difference between being really expensive and incredibly expensive. By 2050, though, it could mean, are you just competitive? Are you definitely competitive? Or are you not competitive at all? So this is the factor to watch when people talk about hydrogen and steel, is what's your hydrogen intensity? Carbon capture is often a controversial one because it's almost always going to be an added cost unless you have a lot of different places that want your CO2 and are willing to pay you for it. So that's why we've pulled back on carbon capture in a lot of our forecasts, because we're saying you really need a good policy environment and you need a lot of supporting infrastructure, transport, storage, people who know how to build these systems. If you have that, steel is in a pretty good position because it's a pretty large emitter. So you already get some economies of scale once you've built several carbon capture plants. And maybe with new technologies, you can bring that cost a little bit lower and start to match it up with kind of some of the subsidies that you're seeing. Right now, the US has the most generous subsidies in the world for carbon capture. But keep an eye on Canada because we think they have an even better subsidy that's about to be introduced. But even with those very generous subsidies, today it's only the very cheapest forms of capture that make sense. And steel is well out of the money unless they pass quite a bit of climate legislation in the US. That's the green line, the bill that they've been trying to pass for over a year now. So CCS really needs policy. It also needs a lot of investment. We were surprised to see that most of the investment in 2020 was actually coming from Europe for CCS. And these are huge mega projects to build that supporting infrastructure that will be needed. In the last few minutes, I want to talk about this sort of moonshot steel technology, which is molten oxide electrolysis. Right now, it is incredibly expensive. We had to change the scale of this chart in order to fit it on there. And that's because it's operating at such a small scale. But it's such an attractive technology to anyone who's thinking about efficiency and simplicity. Because with hydrogen, it's just using electricity in a second-order way. This is direct electrification of the steelmaking process. So an engineer's brain, that's something that looks pretty nice. This is how it works. It's pretty simple. Your iron ore in an electrolyte is just pulled to one side of the electrode or the other. What matters there is the cost of your electricity. So when we were calculating the cost of 24/7 clean power, that came out very different from the cost of just your renewable energy, because you need it every single minute of the day in order to make this process work. Today, it's definitely out of the money. And by 2050, it starts to look a little bit better, but it's still pretty expensive, a lot more expensive than the electricity cost you could get for your EAF. And this is why it's so difficult. The intermittency of wind and solar, you have to smooth that out somehow. So we did a lot of modeling to try and figure out what kind of cost you could get for that and how you could do it. Today, we think the best way is just to plug into the grid for backup, and then to offset that power that isn't clean with excess renewable generation. So you generate and sell more than you need, and you assume that it nets out. So a little bit of fun accounting there. That costs you about $60 a megawatt hour in somewhere like Germany. A bit cheaper in Brazil, a bit cheaper in the US. By 2050, things really aren't much better for your electricity cost. If you're using backup that's provided by hydrogen or batteries, you still have excess renewables generation because it's just very hard to match that line. So people always ask us, why is your electrolysis price higher than your hydrogen cost? And that's because of this. It's because hydrogen is effectively just a way of storing the electricity until you can use it. And we still think that's going to end up cheaper than trying to do 24/7 clean power. What all of this means is that most people think all of these net zero efforts are going to raise steel prices. Customers are already preparing for that. They are talking to their customers about how steel prices are going to go up. They're adding surcharges for carbon prices in Europe. So it's expected that you're going to have to pay a bit more upfront in the short term. But what everyone is hoping is that that investment is going to end up paying off. There have been quite a few numbers that I've heard today about the investment that would be needed for green steel. Ours comes in a lot lower than most other people's, and I think that has to do with when you are making those investments. So a lot of the options that we've talked about today are very expensive. And yes, if we were to transform the whole industry today, that would be incredibly expensive. But if you expect that those early movers are going to create some cost reductions for everyone else, you get to the number that we came to, which is about $280 billion. That's just the CapEx, and that's just the difference in what we expect to be built already. So it's the extra cost of carbon capture, the extra cost of hydrogen. When we put that against the number that we came up with for the total investment to decarbonize the global economy, that number was $172 trillion. So if you go with this number, decarbonizing steel would cost about 0.2% of the total investment happening in the world. And for that, you get an 8% reduction in global emissions. So 280 billion starts to seem like quite a bargain. Thank you very much.
It's great to be here. And as Pinakin said, these are exciting times. After 3 years of COVID, we're all gathered here facing an incredible challenge, and it's great to have all the ideas in the room, from Asovej to Brazil, views from Bloomberg, and of course, our mentor, Contrucci. It's great to be here. And I'd just like to share with you guys today some thoughts about what Valley is doing. Let me see. What Valley is doing. Mouse, thanks. What Valley is doing, what we think could be some complementary technologies for, let's say, the direct reduction electric arc route, and what decarbonisation may mean for markets, for costs, for raw materials. So first, what is Valley up to? What's our thoughts on steel? And to start with, steel is huge for us. It's 95% of our Scope 3 emissions. We've committed to reducing 15% in absolute terms by 2035. That's nearly 150 million tons compared to our business as usual. There's no way we can do that alone. We need to work with everybody in this room. We need to work with all of the scientists to make this happen. I wish it were going to be as cheap as Julia mentioned. That would be great. But there's no way for us to be a clean iron ore company without having clean steel clients. In addition to that, just regarding that, Valley signed more than 20 MOUs with steel companies worldwide. My life is on Teams, talking to them most days of the week. And we also have customer service solutions, trying to develop new relationships with steel companies to work proactively, collaboratively, to find solutions together. Pinakin also said, Contrucci, there's no silver bullet, there's no one way. We're having great fun learning with all of our clients about their different thoughts, their different ways of thinking about it. We also have our Scope 1 and 2 emissions problem. It's tiny by comparison. We have to reduce 8 million tons of CO2 by 2030 to achieve our target of reducing 30% in absolute terms. There's a whole different program, we call it Power Shift, to do that. And one of the bigger things which is relevant to what we do today is the use of charcoal, biocarbon in our pellet plants to reduce CO2 there. And we'll talk a little bit about all of that. So what have we learned when we talk to our clients? And I guess the first thing is everyone's trying to do stuff. Everyone's trying to do stuff now. Everyone's trying to do stuff yesterday. And our industry, the steel industry, the mining industry, is one of huge investments, and it's very difficult to take technical risks. So at the moment, I would say that the consensus proven route to decarbonize is direct reduction, electric arc furnace. You get to use scrap. You get to use hydrogen, as Pinakin says. You reduce something like from 2 tons of CO2 using coke to 1 using natural gas. You can reduce another 300 kilos, something like that, if you deploy CCS. Different to what Julia said, just picking a point, some direct reduction flow sheets already come with a clean flow of CO2 ready to sequester. So there are some options for very low cost CO2 sequestration, depending on where you put your direct reduction plant. And as Julia mentioned, hydrogen is the great white hope, especially in Europe. But I would say consensus worldwide about where steel is going. So Valley has invested in a bunch of technologies. and I'll just like to talk about 4. Invested largely in the people in this room, in Tecnored, in Contrucci, in the professionals, Brazilian professionals. Vale's blessed to be in Brazil, blessed to have great steelmaking partners and experience. And through that, over the last 10 years, we've developed what we believe are some actionable items, some things we can start doing today. Starting with cold briquette. This is the substitute to sinter, the substitute to pellet. Avoiding cooking the stones to 1,200 degrees centigrade. Let's cook them to 200 degrees centigrade. Those pellet and sinter substitutes can be used both in blast furnace, but also in direct reduction. Secondly, in terms of our business mining, for the electric arc furnace, we need high quality iron ore. Once again, another Brazilian technology, New Steel, was acquired by Vale, and we're moving forward with implementing that to produce larger volumes of higher grade feed. Biomass. Ricardo, we have to take on the challenge. There was no biocarbon in Julia's presentation. How can you come to Brazil and not talk about biomass? Guy, next time you come here, we need to get it on your slides. So that's up to us. So we're working on biocarbon. Are you going to Tecnored on Friday, Julia? You have to come. You have to come and see what we're doing. It's great. Trying to make biocarbon a reality. There are challenges about scale. But even in the US, the Department of Energy, 2016 report talks about 1 billion tons of dry biomass. 2017, 400 to 500 million tons of dry biomass available, enough to produce more than 100 million tons of coal substitute just from agricultural residues. Instead of burning it in the field, instead of let it rot in the field, just spending the time and money to convert it into a coal substitute. It's not easy. If it were easy, it would already be done. It's not cheap. As Binakin mentioned, we need more money to do it than using coal, but given the right effort and the right subsidies, it's a reality. And Tecnored relies on biocarbon. This is the reason why we've spent so much time and effort to develop biocarbon. And we believe that Tecnored in particular is a great niche for dealing with steel plant residues that don't benefit from using charcoal, that use dirty coal and therefore is full of dirty contaminants. Talking in a little bit more detail about cold briquettes for the technical guys amongst us. We heat stones to 1,300 degrees. Our pelletizing process is a number of steps, quite complicated. Sintering, simpler, but produces a product that is less easy to transport and has more fines generation when you put it in the blast furnace. So since 2004, some great Brazilian innovators, Rogério Carneiro, ex-Uzi Minas, been in Vale for a long time, Flavio Dutra, Valdeneni. A number of people have been working many years to develop this technology, and we really believe it's ready to go. It has the advantage of being able to work with pellet feed, with sinter feed, reduces CO2, very relevant to China, also reduces particulate emissions, and much better handling characteristics than, for instance, sinter. For the real technical junkies out there, this is the proof in the pudding. This is an acid briquette at softening melting. So this is what it looks like as it passes the high temperatures in the blast furnace. At 800 degrees centigrade, you see the briquettes in perfect condition. And as an acid briquette, it melts down to just over close to 1100 degrees centigrade. When we operate with fluxed briquettes, high reducibility briquettes, we're able to push those temperatures closer to 1,200 degrees centigrade. We really believe this is a huge advantage for the blast furnace. So what have we done? It's been a long journey. The team more or less cracked the code to start off with in 2016. Went through 2 years of a significant amount of effort producing samples to use in charcoal blast furnaces at a small scale. Then the last couple of years, we've been scaling it out with acid briquettes in large blast furnaces. And now this year's challenge is to do industrial trials with a flux briquette, a high reducibility briquette, potential substitute for sinter, as well as a direct reduction briquette for an industrial trial in a DR module. So we've done 6 industrial trials so far in blast furnaces, all very successful, and that is what has given us the confidence to build the first capacity. So starting next year, we'll have 6 million tons capacity ready to go to market. And just as specifically direct reduction and hydrogen is this consensus view, this is the results of 300 baskets that they're sort of mesh bags that you put in a direct reduction furnace. And the results that we've had, this is hot off the press from a couple or 3 months ago, results that replicate what we see in the laboratory, in our development facilities, basically a briquette that is little different, in fact, better metallization than we achieve with our direct reduction pellets for use in a direct reduction reactor. So we're pretty confident that we'll go well with our industrial trial, but watch this space. So as I mentioned, next year we're converting 2 of our pellet plants. We're already changing, and we have 45 million tons of capacity in the pipeline, and some of us inside Valley are always fighting for that to be more. We need to move faster. So, turning the page a little bit, if you're interested in briquettes, I'll just get my plug in. I don't know whether it's already happened or happening, but Rogerio Carneiro has got a presentation on briquettes, and I really recommend you go along. So, yeah, doing my advertising. Dry concentration. We need high-grade iron ore for electric arc furnaces. It's not easy. There are constraints on geology. There are constraints on tailings dams. Once again, new steel. Mauro Yamamoto, another great Brazilian inventor, came up with a dry magnetic separation technology, which we're implementing as we are here today at Vargem Grande, and also have a pipeline to expand capacity to supply more feed for direct reduction. No water, no tailings, and in fact the byproducts are high-grade sand for the cement industry, all moving in the right direction. So, biocarbon. Back in 2013, I remember having dinner or lunch with Marcus talking about we need to move Tecnored across to biomass. I came to Brazil in, I think, 2001, and I fell in love with elephant grass back in 2003, falling in love with a plant. It's got to be a solution, and it's a great solution, not only from an environmental perspective, but also in terms of developing wealth in rural communities, jobs. Sometimes people see it as a challenge to biodiversity. It can be, in many ways, a solution. Brazil already has millions of hectares of degraded land. The production of biomass can be the lifeblood to bring wealth to rural communities, to pay for the reforestation, much more so than any environmental devastation. So we need to make it work. As Pinakin said, we need money. It costs more than coal at the moment. So we need those subsidies, but the route is economic. The costs are not significantly different to CO2 sequestration. The challenge is scalability. We've developed in Tecnored our own carbonization technology, building off a number of others. And for those that will be visiting the plant on Friday, you'll get to see the plant. We're in dry commissioning as we speak, 25,000 tons a year. We believe it has some advantages over the existing technologies, but all of these carbonization technologies, new ones for processing agricultural residues, are not yet at scale, and there needs to be a considerable effort to make them productive. But we're on the way. As I mentioned, so I mean, for those that will visit on Friday, this is what you'll see. It's a first step. If this works, we at Valley will be going ahead, building a bunch more. As I mentioned, we need a lot of biocarbon to reduce the CO2 in our pellet plants, and this is the path for us to achieve that. But obviously, beyond our internal requirements, we see great opportunity for use in the blast furnace. And last but absolutely not least, Technored. Technored, to be a low CO2 solution, needs biocarbon. So unfortunately, there's a little bit of a bottleneck. Currently, the global ocean-traded biomass market is about 25 million tons, essentially driven by European power subsidies. There is scope for a great deal more, as I mentioned from the Department of Energy report. But in the meantime, whilst biocarbon is not available, we believe that Technored has a particularly useful niche to use coal to process steel plant residues, particularly in China, where the steel business, China has built 1 billion tons of steel capacity over the last 20 years, and there is limited capacity to process the steel plant residues. So in the meantime, whilst the biocarbon capacity is being built out, we see a great opportunity there. But in terms of action, it's a reality. It's being built as we speak. We started land clearing in Pará, being a neighbor of Ricardo, on our new Technored plant, as I say, last month, April, 2 months ago. So, changing gear a little bit, and moving on from technology and talking a little bit about some of the constraints, and the constraints in particular around raw materials for the EAF route. It's a race. It's a race to zero. All the steel companies, or the world leading steel companies, have announced targets tending towards zero in 2050. It's interesting, many times when I talk to people, they say, will the steel companies really get there? Julia puts out a chart saying none of them will, they're lying, aren't they? I mean, your line goes higher than that in 2050. So are we going to get there or aren't we? And it's interesting, there's a lot of pressure. Shell was taken to court in Holland for greenwashing or green-wishing or whatever you want to call it. But it's a real thing. We feel it in Valley, and every large company, every listed company faces a lot of challenges to reduce their CO2. So it's kind of in that world, everyone's making promises. No one is quite sure how to meet their promises, but suddenly everyone's being held to their promise. So will we get there, won't we get there? I think we will. But what's been announced so far doesn't get us there. Europe is certainly ahead in terms of announcements. There's a lot of policy support. You see 34 million tons of direct reduction announced for Europe by 2030. That's 50 million tons nearly of direct reduction pellet. That's what it means for Valley, and obviously our companion iron ore suppliers. But is it really going to happen? As far as we're aware, there is still no direct reduction plant under construction in Europe. So it's a lot of announcements and not yet happening. And now, obviously, with the Ukrainian war, there's a lot of doubt about natural gas. You start thinking about importing LNG for direct reduction in Europe, and you start getting into conversations about methane leakage. That was a huge issue at the beginning of the last COP. And so there are challenges. JKT and China are much more conservative in making their announcements. We feel the urgency when we talk to our clients. And in fact, in China, there is action. There are 3 direct reduction plants under construction using coke oven gas, but to learn how to use direct reduction and hydrogen. And China is a huge beast. In terms of global pig iron, 1.4 billion tons of pig iron produced each year. 2/3 of it, 900 million tons, is produced in China. So the amount of direct reduction that would be required to solve China's issue is huge, whether it's using natural gas, hydrogen, CCS. So, some thoughts. I mean, this is just, for instance, the numbers from Europe as announced. As I say, up until now, the announcements are all for European-located direct reduction. The question is, with the challenge around natural gas, with the challenge around green electricity supply in Europe, are all of these plants going to be built in Europe? Is there space? I think Julia presented low-cost hydrogen in Brazil, low-cost hydrogen, or electricity at least, and hydrogen in the US, in the Middle East. Where is the best long-term place to build these direct reduction plants? So we believe there is the potential to move to hubs, to gain the advantage of scale by building a lot of these direct reduction plants in single locations with integrated infrastructure. And so we may see the world migrating to a world of hubs. Once again, thanks very much, Contrucci, you presented in your graph of iron ore use, starting with lump and then sinter. One thing that wasn't on there, that prior to the Second World War, the Europeans produced steel with European iron ore, not with Brazilian iron ore, not with anybody else's iron ore, with European iron ore, and then over time became dependent on Brazil and Canada, etc., etc. And maybe now we're in another transition where we move from depending on overseas iron ore to overseas iron, turning the iron ore into iron where the low CO2 energy is the cheapest, where there's natural gas availability so you can get started, where the price is low, where you have land-based CCS. Sequestering CCS on land is significantly cheaper than pumping it out to underground locations at sea, and where in the future hydrogen will be competitive. But that's going to require, for the electric arc furnace, a huge amount of direct reduction pellet. Pellet feed is a huge challenge for us. The environmental licensing of tailings dams in the aftermath of the two tragedies in Brazil is huge. The pellet market has been further impacted by the recent war. Russia, Ukraine account for 30 million tons of exports. And just recently, India has shown an intent not to export pellets by imposing an export tariff. So where is the raw material going to come from? And where's the quality going to come from? Valley is blessed with great quality of iron ore, as my colleague from ArcelorMittal said at the beginning of the day. But the rest of the world isn't so much. So there is a huge challenge to come up with enough high quality iron ore for the electric arc furnace. But maybe working slightly differently with electric arc furnaces, working with briquetting of high quality sinter feed that Valley has in Carajás, maybe we can find a competitive route for DRI, EAF, that route, and the volumes are significant in terms of supply. So, in summary, what can we do to start? Low CO2 agglomerate, pelletizing and sintering represent nearly 10% of the CO2 emissions for the blast furnace, more than that for the direct reduction route. We can get started by converting across to coal briquettes. Once we can prove this consistently industrial scale, it's a great opportunity. It's also an opportunity to take Brazil's high-grade sinter feed and make that available for electric arc furnaces. Many technical challenges, but great opportunities. Dry concentration, new technologies. I mentioned our in-house technology, but we don't stop there. We're looking at every opportunity to find better ways to produce higher quality iron ore or iron oxide to supply better volumes to the market. Biocarbon, get the plant working in Pinda, build it out, and demonstrate to the world that biomass is really a route, as Verde do Brasil has said. I mean, I've seen Ricardo's presentation a couple of times. It sometimes feels like the world doesn't want to listen, but it's the truth. It's a great opportunity. And Technored. It's we'll get there. We'll get there finally. Your legacy is safe, Marcus, and we'll have great fun going there. Thanks very much, everybody.
Thank you, Steve. Another great presentation, lots of efforts, and I second him that BNF now needs to take into account biomass. I believe it was a great learning for you, Julia, today. Sorry for putting you in a hot spot. In the middle of the two biomass guys now. But thank you very much again. With that, we come to the conclusion of our opening ceremony and a great plenary session. I believe we had 5 great speakers, a super lineup, and the conference will continue. But before I finish, I want a round of applause for the people of ABM. So now here represented by Miriam, they are the ones that sit on the back, but do all the heavy lifting, all the hard work for us to make the conference a big success. So Miriam, where are you, Miriam? Over there. Congrats for Miriam and the whole ABM team. ABM is a big family, a big community. So it's a wonderful opportunity for us to be around, discuss our industry, and develop into something which is more competitive, more agile, greener, and etc. I hope the plenaries will stay around. So if you have any questions or you want to interact, I invite you to touch base with them in the sideways of the conference. And now we have a break. We will come back at 2 o'clock. Don't eat too much, because we still have a lot of good presentations. I don't want anyone sleeping over it. Okay, thank you very much.